the conductivity of all ions furnished by 1 mole of electrolyte. Okay, 1 mole of electrolyte, and if 1 mole is present in whatever may be the volume, 1 liter, 2 liter, you are not bothered about the volume. Okay, you are bothered only about 1 mole. That is the molar conductivity. Molar conductivity, or molar conductance, is the specific conductance into 1000 by molarity. Okay, that's what we had seen in the last class. So we have seen that the molar conductance is basically kappa into total volume in which the 1 mole is present. Kappa into 1000 by molarity. That's what we have seen. Now we are going to see the effect of dilution on molar conductance. You have taken 1 mole of NaCl, right? And 1 mole of NaCl is present in 0.01 liter, 0.1 liter, 10 liter, you are diluting. What is happening to kappa? With dilution, as the dilution increases, the volume increases, okay, kappa decreases. Kappa is basically the specific conductance, the conductance of 1 cubic centimeter of an electrolyte. Okay. So as you are putting more and more water, the ions are spreading in a larger volume. But as far as kappa is concerned, you are bothered only about 1 cubic centimeter. So in that 1 cubic centimeter, the number of ions decreases. So conductivity or specific conductance decreases with dilution. Got it? As you are having less number of ions available in 1 cubic centimeter. But the molar conductance increases with dilution. Don't put these type of arrow in your board examinations, okay? I am just putting it to write it quickly, but don't use this type of arrows. Your marks will be deducted, okay, in your examination. Be careful. Okay, you have to write the complete statement. Is it clear, Marwa?
Yes, sir.
So with the increase in dilution, when you are putting more and more water, molar conductance increases. So Jasleen, Aisha, can you tell me why the molar conductance increases though you have just 1 mole of electrolyte? What could be the reason? In order to understand the reason, we have to look at the electrolyte in 2 different ways. Okay, the electrolyte can be strong electrolyte or it can be weak electrolyte. So why the molar conductance increases with in addition of water, Aisha? What could be the reason? It is because as you are putting more and more water, okay, though you have just one mole, but the ions are able to conduct the electricity with more ease. What is the reason? Okay, to understand the reason, you have to there is a separate reason for strong electrolyte and separate reason for weak electrolyte. For strong and weak, the reasons are different. So first, what are strong electrolytes? Strong electrolytes like HCl, NaOH, KOH, right? Their alpha is 1, almost 1. Means they are 100%, their dissociation is almost complete. They are almost 100% dissociated. 100% dissociated because they are strong electrolyte. Okay. And when you are adding water, the molar conductance increases. It is because as you are putting more and more water, suppose the ions are getting separated. They are moving farther from one another. Suppose you are having a small volume of NaCl. Okay. You have Na plus Cl minus, Na plus Cl minus, Na plus Cl minus, Na plus Cl minus. Very small volume. Okay. And when you apply, when you put the electrode, the ions start moving, and because the ions are in a very small volume, they are going to stop each other. Is it clear? Suppose this positive ion is moving like this. Negative ion is moving like this. So it is going to attract. Okay. And they're going to collide with each other in a small space. So a strong electrolyte, the molar conductance increases because with the dilution, the ions are separated. Okay. And if you have more volume, let's say, if you take a bigger volume, so the ions are farther, and they are not going to stop each other while moving in opposite direction. Is it clear? Jaslene, Aisha, is it clear that when you put water to the strong electrolyte, the molar conductance increases. Molar conductance is the conductance by 1 mole of electrolyte. Okay, though the ions are same, and because it is a strong electrolyte, it is 100% dissociated also. The ions are same, but if I put more and more water, the ions are moving away from each other because you are having larger volume. So as you are putting more and more water, the molar conductance is going to increase. It is going to be more and more. For weak electrolytes, Weak electrolyte do not dissociate completely. Okay. Weak electrolyte like acetic acid. So Jasoline acetic acid is a weak acid. And it do not dissociate completely. Dissociation may be 10%, 5%. Okay. Out of 100, only 5 molecules dissociate into H plus and acetate ion. It is a weak acid, weak electrolyte, or ammonium hydroxide. So what happens to them? When we put water, upon dilution, volume increases. And initially alpha was much less than 1. Alpha is the percentage of dissociation or degree of dissociation. Okay. How much they dissociate? Because they are weak acids, so they do not dissociate into H plus. They remain as it is. So alpha was very less. Okay. But as you are putting more and more water, the volume is of the water, the solvent is increasing. Alpha increases. More ions are generated. Due to increase in dissociation upon dilution. And if you have more ions, you will have more molar conductance. So lambda is going to increase for both, for weak electrolyte also, for strong electrolytes also, but the reasons are different. So Jasoline, Aisha, have you understood the reasons? Tell me quickly.
Yes,
For
sir.
strong and weak electrolytes, strong electrolyte, they are already dissociated. So there is no point of increase in dissociation of alpha. But when you put more and more water, the ions are moving away. And if they are moving away because oppositely charged ion, when they conduct electricity, they move in the opposite direction. So if the volume is more, they can travel more easily without causing disruption into the movement of each other. In a small volume, they will collide with each other. The molar conductance is going to be less. In a small volume, when you add more water dilution, the molar conductance increases with dilution. For strong electrolyte or weak electrolyte also it increases. And the reason is that the weak electrolyte are actually do not dissociate completely. They dissociate very less into their ions. So when you put more and more water, and you are increasing the volume and more ions are being generated, their alpha increases. Okay, do remember this. This is a very important point. Their alpha increases, degree of dissociation or percentage dissociation increase, ions, number of ions increase. And because of the number of ions are increasing, their molar conductance, though you have put 1 mole, but 1 mole doesn't mean that all 1 mole will dissociate into ions. Okay, it depends upon the degree of dissociation. Okay, and let me tell you very important point which we have seen over here, which is suppose if you are increasing the dilution, the molar conductance is increasing. Okay, this is the molar conductance of NaCl is increasing. upon dilution. It keeps on increasing, it keeps on increasing if you keep on adding water. But at a certain point, a limit is reached, and that is known as lambda naught m NaCl, or it is known as lambda What does this mean? Increasing dilution, addition of water, lambda is increasing, but doesn't mean that lambda will become infinite. Okay, molar conductance cannot become infinite. It is not a superconductor. Okay, so it reaches its maximum value. Okay, for each salt, it reaches its maximum value, and this maximum value maximum value of a molar conductance of a compound. So Marwa, this is known as limiting value of molar conductance. It is represented by lambda naught. In the bracket, you write the name of the compound for which you are measuring. M represent the molar conductance, and or it is represented by lambda infinity. That is at infinite dilution. Molar conductance at infinite dilution. So what do you mean by limiting value of molar conductance? It is the maximum value of molar conductance attained for a given compound at infinite dilution. Is this clear, the definition? Nesline, Aisha, Marwa, is it clear?
Yes, sir.
Maximum value of molar conductance, because as you are putting more and more water, the molar conductance is increasing. But what will be its maximum value? That is a very important point. So maximum value is represented by lambda naught or lambda infinity. Okay, maximum value of molar conductance. Got it? Clear? So how to find it out? That's the problem. Because suppose if I'm putting NaCl in water, I need to have idea at what could be the maximum value of molar conductance of 1 mole NaCl. Molar means 1 mole NaCl. Or if I'm making an acetic acid solution by putting 1 mole in any amount of water, by adding more and more water, the molar conductance is going to increase. But I need to understand that what will be the maximum value of molar conductance. Is it clear? And that maximum value will be denoted by lambda naught or lambda. Marwa, is it clear? So
Yes, sir.
this is denoted by, because you are having exam and it is being asked, I think So let's and this is a very easy topic, but most of the student may skip it. So let's all of you tell me if there is any problem, if you feel so. So we are interested in the maximum value. What is the maximum value of molar conductance? Because we need to know that how much molar conductance 1 mole can show, and what is the maximum value it can have. So again, I will tell you to split the problem in two different categories. That is for strong electrolyte and for weak electrolytes. And as you can see, all of you can see, this is for the strong electrolytes. Is it clear? Strong electrolyte like NaCl, KCl, okay, they are already completely dissociated. Okay, they are already present in the form of ions. Okay, NaOH, HCl. So for these strong electrolytes, the molar conductance increases with dilution. This is the molar conductance. Conductance of 1 mole of electrolyte. It is increasing with dilution. Okay, dilution is increasing, the concentration is decreasing. So if you are moving in this direction, dilution is increasing. You are putting more and more water. The concentration is decreasing. Okay, because when you are putting water in just 1 mole, it is becoming more and more dilute, so concentration is decreasing. So that's why this root C, this is x-axis is square root of the concentration. And when you are increasing the dilution, the concentration is decreasing. The square root of the concentration is decreasing in this direction. Are you getting my point? So this is the molar conductance. This is as you are putting more and more water, concentration is lowering, volume is increasing, and you can see the molar conductance is increasing. It is becoming higher and higher. Can you understand the graph? What I'm trying to explain it to all of you. That is just for 1 mole of NaCl. 1 mole, let's say you put it in half liter, 1 liter, 2 liter, 5 liter, 10 liters. Is it clear? So concentration is decreasing. Molarity is decreasing. But it is still 1 mole, so molar conductance that is increasing, and it will attain its maximum value. Is it clear? This is the maximum value. This is the molar conductance at infinite dilution. Lambda naught or lambda infinity also you can call it. For any given compound, HCl or whatever the compound which you are studying. And this is for a strong electrolyte, as I told you. And this equation, and this is very easy to make out what is the maximum value of, what is the limiting value of molar conductance. Very easy to figure out. Because the graph is linear. Okay. And we love linear graph, we love straight lines because they are very easy to predict. At what point you will have what value. Once you have the equation of straight line, you can easily predict what is the value, what value of x and what value of y. For that, you can easily make out. And for a strong electrolyte, I would like to say this is a straight line graph. Straight line graph between, this is between molar conductance and the square root of concentration. Is it clear? This is the straight line graph, right? And a straight line, this is y-intercept. Y-intercept is the maximum value that lambda can have. And you know y equal to mx plus c. So y-axis you have the molar conductance, x-axis you have the square root of concentration. Slope is minus a. And c is the intercept. This is y equal to c. C is the intercept on the y-axis. And this is the slope. Slope is negative means it is coming down, and if you are decreasing the concentration, it is increasing. Is it clear? So this is known as Debye-Huckel equation. Has everyone understood this? Tell me quickly. Clear? So Debye-Huckel equation help us to know the value of limiting value of molar conductance of limiting value of molar conductance. What is the maximum value of molar conductance for a given compound? Okay, that is that can be predicted by Debye-Huckel equation, which is none other than a straight line equation. Okay, between the molar conductance and square root of the concentration. Lambda m is equal to lambda naught minus AC. A depends upon the nature of the electrolyte and the solvent. For each electrolyte and a solvent, you have a different value of A that will be given to you, that will be provided to you. Okay, so you can figure out the value of A. Okay, it is a constant for each electrolyte. Is this clear? But for a strong electrolyte, it is very easy to figure out the limiting value of the molar conductance, because it is a straight line function. A straight line can be easily calculated. So I have given you the summary of what is happening over here. I told you earlier also, and here you can see what is the what is happening. So as but you will not use these arrows, upward arrow or downward arrow in your school examination. Be careful. I have given you because just to save the space and move forward quickly. So this is basically the dilution is increasing. For strong electrolyte, this is valid only for strong. Separation between the ions is increasing. Interelectronic forces of attraction is coming down because they are separating, cation and anion are separating away from each other. The ions can now travel more easily, ionic mobility is increasing, and molar conductance is increasing when you are putting more and more water, and it reaches its maximum value at infinite dilution or at zero concentration. But and that value, maximum value, is known as lambda infinity or lambda naught. Is this clear? Right?
Yes, sir.
Very simple. Debye-Huckel equation. So, and A is a constant. Okay, A depend upon the nature of the electrolyte. For example, NaCl is 1:1 electrolyte. KCl is also 1:1 electrolyte. So A will be same or particular type of electrolyte. Is it clear? So very easy to figure out this. And now we will. So this is sorted out, but this is only for strong electrolytes. The problem, half of the problem is solved. The another half of the problem is still left. Okay, the another half of the problem is related to weak electrolyte. Okay, weak electrolytes. For example, if you have acetic acid, organic acid do not dissociate completely. And they will dissociate very less into their ions. But as you are putting more and more water, okay, there are dissociation degree of dissociation means out of 1 mole how much has dissociated. Okay, suppose alpha is 0.5. Alpha is the degree of dissociation. Means out of 1 mole how much are dissociated? Half, it is half. So out of one, half of the acetic acid is dissociated as H plus and acetate, right? But degree of dissociation, as we are putting more and more water, the volume is increasing. The volume of the complete solution is increasing, and alpha is increasing. So you have put 1 mole, but 1 mole has not completely dissociated. But as you are putting more and more water, the degree of dissociation is increasing, alpha is increasing, and more ions are being generated. I'm not putting more acid. Be careful. I'm talking about molar means 1 mole. But how come you have more ions being generated? It is because the acid which you have put was initially undissociated. Now it is addition of water is causing more and more separation of ions. So more ions are being separated. Is it clear? More ions are being formed. So if ions are being formed, the molar conductance is increasing. At a given concentration, and it reaches its maximum value. This is known as limiting value of the molar conductance of acetic acid. But the problem is the graph. Okay, the nature of the graph. The nature of the graph is not a straight line graph. It is very weird, just like this. Okay. And we are comfortable with the straight line graph, but we are not comfortable with these kind of graph. So for weak electrolyte, as you are decreasing the concentration is decreasing in the backward direction. A molar conductance increasing. What will be the limiting or the maximum value of the molar conductance? It is not a straight line graph which can tell us that it is intersecting at a particular point. It is just moving like this, and it appears that there is no end to it. But that is not true. How to figure out what is the maximum value? Is it clear or not?
Yes.
So what is the maximum value? We can't figure out. But there it was very easy. There it was just a straight line. So wherever the lambda m intersect the axis, y-axis, that is the maximum value. And you can figure out lambda equal to lambda naught minus a root square root of the concentration. Okay. This is quite weird. So now graphically we can't determine it. We need to use something else, because graph is telling it is like this and we are not able to calculate it. So we need to take the help of a new law which is known as Kohlrausch. Kohlrausch law can be applied for all, for weak and strong, though it is must for weak electrolytes. To determine, it helps us to determine what is their maximum value of molar conductance. Weak electrolytes, and I have written all the things. Weak electrolyte are not completely dissociated. The extent of alpha increases with the increasing dilution. The limiting value of the molar conductance cannot be found out with the graph. It can be found out with the help of Kohlrausch law. Okay, what is this Kohlrausch law? Okay, and it is going to make the life very easy for us. Okay, very simple. Okay, so Kohlrausch law tells us that whenever you put a lot of water into a solution, right, whenever there is infinite dilution, okay, whenever there is a lot of water, whenever there is infinite dilution, and whenever the dissociation is almost 100% complete. Okay, for weak it is 100% complete, and strong was also 100% complete, because strong electrolytes are already dissociated completely. So all the ions get separated when you put a lot of water, because there is a lot of space to move away. Okay. So at this infinite dilution, whatever the electrolyte is there, that is present in, that is being dissociated into ions, and each ion behaves separately, not at any other concentration, only at infinite dilution. And each ion makes its own contribution towards the molar conductance of the electrolyte, irrespective of the nature of the other ion present with it. Is it clear? Let me explain it to you. Suppose you have taken potassium chloride and you will measure the molar conductance of potassium chloride at some concentration C, which is not infinite. Let's say it is 0.1 molar. When you are putting more and more water, the molar conductance is increasing. Lambda and KCl 0.01 molar. This is more. Okay. And when it reaches its maximum value, this is a maximum value. And at this maximum value, the potassium ions are completely separated from the chloride ions, because there is a lot of water. Even if you take talking about the acetic acid is will completely dissociate into acetate ion and H plus ion at infinite dilution. So at infinite dilution, each ion will contribute towards the molar conductance of the complete electrolyte. So KCl, don't think of KCl, think of K plus and think of Cl minus, because now they are not together at infinite dilution, they are separated, completely ionized. So molar conductance at infinite dilution will be equal to the sum of the molar conductance of individual ions. That's the summary. Have you heard it? What I said? Very important. Kohlrausch law. In just few words, I will summarize. A molar conductance of an electrolyte at infinite dilution is equal to the sum of the molar conductance of its individual ions. Is it clear? So let me explain it. Suppose if you take KCl, the molar conductance of KCl when at infinite dilution will be equal to the molar conductance, sum of the molar ionic conductance of individual ions at infinite dilution. This is small lambda. This is for individual ions. Is it clear to all of you? It happens only at infinite dilution. Doesn't happen, let's say, suppose if I take 1 molar concentration. Aisha, Marwa, is it clear or not?
Yes, sir. Yes, sir.
At 1 molar concentration, Jasleen, This is not equal. Because this is not infinite dilution. You require infinite dilution to ensure that all the ions are very far from each other. And then when they are at infinite dilution, they can travel freely, okay, with their own speeds. And that let us conclude that the molar conductance at infinite dilution can be taken as the sum of the molar conductance of individual ions. That is at infinite dilution only. Is it clear? Not at any other concentration. Look, I have put not equal to sign. So if I talk about the molar conductance of means 1 mole calcium chloride. Okay. So it will be equal to the sum of the molar ionic conductance. Molar ionic conductance means small lambda, and that is at infinite dilution. Either put the not or put the infinite sign. Is it clear? So at infinite dilution, put the not sign, or the molar conductance of calcium chloride as a whole will be equal to the sum of the molar conductance of calcium ion and chloride ion, because chloride ions are present as in 2 mole. Okay, so twice of the molar conductance of limiting value of the molar conductance of the chloride. Is it clear? So potassium ion, whether it is KCl or KBr, the molar conductance of the potassium ion is going to be constant, and that is at infinite dilution. Okay, when they are completely separated. So each ion has its own molar conductance. That is the maximum value of ion. That maximum value of ions, each individual ion can be summed up, and that can be used to find the molar conductance of the complete salt. Is that clear to everyone? Is it clear or not?
Yes, sir.
So this makes the life very simple. The molar conductance of a compound, complete compound, don't need to worry about the compound. You can treat them as individual ions. And as per the formula of the salt, you can multiply the molar conductance with their number of ions present in 1 mole of the salt. And you can easily figure out, you can find any value. Okay, and you can add and subtract. You can treat them like ionic equations. Okay, ionic equations. Suppose if they give you some molar conductance of known compounds, you can add and subtract to get to make a new formula and get the new value of the molar conductance. So very easy, Paul-Roche law. Okay, and very easy to apply. Okay, and NCRT has given the values of the molar conductance also. Right. So so I have told you the basic idea, and with this you can easily solve all the problems. Okay, just once again I would like to draw your attention. I have written the limiting value of the molar conductance at infinite dilution of an electrolyte, means the maximum value for the electrolyte for a salt is equal to the sum of the limiting ionic conductivities, molar ionic conductivities. It is equal to the sum of the limiting values of the molar ionic conductivities of individual ions of cation and anion. and each has to be multiplied by the number of ions present in one formula unit of the electrolyte. So here I have shown you for aluminium sulfate, it is not equal to the aluminium and sulfate ion. No, because there are 2 mole of aluminium ion and 3 mole of sulfate ions in the formula, you can see. So limiting value of the molar conductivity, because it is molar, you need to multiply by mole. Is that clear? So molar conductivity of aluminium multiplied by 2, molar conductivity of sulfate ion, and that is applicable only at infinite dilution. Is that clear? Infinite dilution means when you have complete dissociated, when they are completely dissociated, 3 times the molar conductivity of sulfate ions. For example, if you talk about the sodium sulfate, the limiting value of the molar conductivity will be equal to twice the limiting value of molar conductivity of Na plus ion. Twice, why twice? Because you have 2 moles of Na plus and plus limiting value of molar conductivity of sulfate ions. Sulfate you don't have to multiply by 2 because sulfate is actually just 1 in the formula. Similarly, if you look at the molar conductivity of barium chloride, okay, it is equal to the sum of the limiting value of molar conductivity of barium and twice the limiting value of the molar conductivity of the chloride ion, because you have 2 chloride. But you should remember that is only at infinite dilution. Is it clear?
So how do we like identify if it's completely dissociated?
No, it is. You should look for this symbol. Is it clear? Or this symbol or this means infinite dilution. A lot of water is there. So when they are present in infinite dilution, means you will assume that they are completely separated. Got it?
So
Okay. But there is one more thing which you need to know, that it should be a soluble salt. Okay. If it is insoluble salt, then it may not undergo 100% dissociation, because that will form a PPT, precipitate. All these salts are completely soluble in water. When you take lot of water, they are soluble. Why they are soluble? Because their ions are completely away from each other. They are completely dissociated. Is it clear? And that's why they are contributing maximum towards the molar conductivity, molar ionic conductivity. Each ion is contributing maximum towards the molar ionic conductivity. Barium chloride at any other concentration, C, that could be 1 mole, 2 mole, okay, 2 molar. This is not valid, okay, because this is not infinite dilution. Is that clear to everyone? Any doubts? Aisha, Marwa, Jasleen, tell me quickly. So this I'm going to write not Ca2 plus plus twice of lambda naught. This is small lambda for ion, capital lambda for complete compound. Got it. Like this. Okay. So these are the further application of Ulrauch's law. Okay. Before moving on to the applications, okay, let's try to figure out how they are same. Why the two sides are same, are having the same value? Can you tell me? Why the two sides are having same value? So on the left hand side you have potassium chloride and sodium chloride ion. On the right hand side, Jesslyn, you have KBr and NABr. And I have put an equal to sign in the middle. Means they are same. The difference is same. Okay, I'm not telling that for KCl is equal to KBr. Not like that. I'm telling you the difference of the molar conductivities of KCl and NaCl is same as that of the difference in the limiting value of molar conductivity of KBr and NaBr. How can you prove it? Are you getting my point?
Yes, sir.
So just split the compound into individual ions. Okay. So this is K plus and Cl minus. Minus Na plus and Cl minus. So the molar limiting value of the molar ionic conductivity for Cl minus will get cancelled. Similarly, limiting value of molar ionic conductivity for Br minus will cancel. Okay, because they are there. When you, this is going to happen when you split the salt into its compounds. Is that clear? So you will have K plus and Na plus. Difference of K plus and Na plus on the left hand side. Similarly, your difference of K plus and Na plus on the right hand side. That's why it is. Similarly, NaBr and NaCl. If you take the difference, Na will cancel, it will be Br and Cl will be left. Okay. And that will be same as that of KBr and KCl. This is KBr and KCl. KK will get cancelled. Is it clear? You will have the Br and C, difference of Br and C. So I hope this is clear to all of you. This is the table which is given in NCERT. Okay. Molar ionic conductivity of individual ions. So it doesn't matter whether the Na is with Cl minus or Na is with Br minus, whether it is Na plus, NaCl, NaBr, NaI. Okay, as long as it is completely dissociated at infinite dilution. Na plus will have this fixed value of molar conductance at a given temperature. Limiting value of molar conductance of individual ion. This is known as molar ionic conductivity. Limiting value. Limiting means at infinite dilution, the maximum value. Whether it is NaCl, whether it is NaBr, NaI, you don't have to worry. At infinite dilution, Na plus will have 50.1 value. And they will be given in the question. So don't worry about that. You can notice one more thing, the H plus is having a maximum value. H plus can travel very quickly. So it can transfer the charge very quickly. So it is having the molar ionic conductivity near about 350 Simon per centimeter square per mole. Similarly, among all anions, the OH minus hydroxide anion is having the maximum value of the molar ionic conductivity. If you have bigger or larger anions, they are going to move very slowly. And their molar ionic conductivity at infinite dilution means their limiting value is going to be very less. You can see for acetate ion, it is very less. Got it? So I hope this is clear to you. Okay. Any doubts in this? And now we will come to the problem of that we were stuck in how to get the molar limiting maximum value for molar ionic molar conductivity for a salt. we were stuck. For a strong electrolyte, it was quite easy because it was a straight line graph. Lambda equal to lambda naught minus A root C. For weak electrolyte, the graph was completely weird and we were not able to figure out how to get the maximum value of the molar conductivity. So now it is easy. At infinite dilution, you know, acetic acid is going to be completely dissociated to acetate and H plus ion. So its molar ionic conductivity will be the sum of the molar ionic conductivity of acetate ion and H plus ion. That's it. Okay. So limiting value, the graph was not helping us to know. The graph is telling that it is going to go much higher. No, not like that. We know the limiting value of, now we know. And who helped us to know this value? Kohlrausch law. Is it clear to everyone? Very simply, I am putting it. The limiting value of the molar conductivity of acetic acid at infinite dilution. At infinite dilution, be careful, is equal to the sum of the limiting value of the molar ionic conductivity of the acetate ion plus the limiting value of the molar ionic conductivity of the H plus ion. Is it clear? So sum of the, now we don't have to rely on the graph. The values of the individual ions will be given to you. Okay. So now it is very easy, or sometimes they will give you compounds so you can add and subtract them to get the values. Okay, and it has become very easy to do this calculation. Okay, let me give you a question. Limiting value of molar conductivities of NaCl limiting value of molar conductivity of HCl is provided in the question. It is 425.9. Limiting value of molar ionic conductivity of sodium acetate. So these limiting values for sodium acetate is given. Let me write it. For sodium acetate, it is 91 Simon centimeter square per mole. The units are same for all of them. And what they are telling us to find the limiting value of the molar conductivity of acetic acid. Is it clear?
Yes, sir.
What it is going to be? Aisha, Marwa, Jasleen, how you are going to do this problem? Tell me quickly. If they would have given the limiting value of molar conductivity of H plus ion and acetate ion, then we would have added both of them to get the molar ionic conductivity of acetic acid. Here, but they have not given, or if they would have given this table, then you will take is a 350 and acetate is 40. Okay, 350 and 40, it will be somewhere around 390. If they would have given the values, but they have given some entirely different values, not of H plus and acetate ion, but they have given the values for HCl, NaCl, and sodium acetate. So as I told you, at infinite dilution, all ions are completely separated. And you are going to treat these compounds as combination of ions. And you are going to make an expression which can by adding and subtracting the molar ionic conductivity of these compounds, such that you will get a you are left with only with H plus ion and acetate ion. Okay, so how can we get acetic acid? Okay, it is actually equal to, ideally they should have given it like this. But because they have not given us like this, that doesn't mean that we will not attempt the problem. We will attempt it. Okay? So we will try to add and subtract these compounds such that we can get these two ions finally after cancellation. Got it? So let's start. We need acetate ion. So let's write this. We need H plus ion. H plus ion is there in this compound. So let's add this also. We need acetate ion. Okay, no, this is so I should write this sodium acetate. We need acetate ion, we need H plus ion. So I have taken the sodium acetate for the acetate ion and HCl for the H plus ion. But along with this sodium also came in, Cl also came in, which I don't want. I want that acetate and H plus ion. So I need to remove the molar ionic conductivity of Na plus and Cl minus. So in order to cancel them, I will subtract the molar ionic conductivity of NaCl. Are you getting my point or not? Is everybody getting my point? Marwa, Jasleen,
Yes, sir.
Aisha.
Yes.
So what do we subtract?
Yeah, we will subtract. So we need acetate and H plus. So for acetate, we took this one. For H plus, we took this one. But along with these two, Cl minus and Na plus ions also came in. So in order to remove the Na plus and Cl minus, I need to subtract this. I need to subtract the molar conductivity of NaCl from these two. Got the point? So this will be, or you can split it and figure it out. This will be acetate and Na plus. I will write it in a short form, acetate ion plus Na plus. I'm not writing the lambda. This will be H plus and Cl minus. So I need this, but I don't need Na and Cl. So I subtracted NaCl. So minus Na plus. I'm not written lambda, I'm just writing the ions. Okay. Don't do this in your examination, your marks will be deducted. write complete lambda not ACO minus. Okay, so this will get cancelled. Marwa, is it clear? Aisha, is it clear? Jaslin, is it clear?
Yes.
Yes,
So
sir.
ultimately, by adding and subtracting these compounds, you will them in such a way so that you are left with the anions and cations finally, for which the molar ionic conductivity is asked. Okay. For whatever the formula, the molar ionic conductivity asks, you need to add and subtract, just like algebraic equations. And so, and you will accordingly add and subtract these values also. For sodium acetate, it was 91. And for HCl, it was 426. I am taking it as 426. And for NaCl, it was 126. So plus minus 126. Okay, 126. This is. I'm taking the rounded off values, not taking the decimal to make the calculation very easy. This is 391. Got it. Other way to do this problem is that if they would have given the table, if they would have given the direct values of H plus and acetate, you can add them. This is 350 and 40.9. So again, it is 391 only by direct addition. But indirectly, if they will give, you have to do it in this. Okay. So just let me do one more question. Which of the following is the correct representation of limiting value of the molar ionic conductivity of NH4 ammonium hydroxide? So you are provided with the limiting value of NH4 Cl as X. You are provided with the limiting value of NaCl as Y. You are provided with the limiting value of NaOH. So can you tell me what is the value of limiting value of the molar conductivity of ammonium hydroxide in terms of the molar conductivities of ammonium chloride, NaCl and NaOH? No need to do the calculation, just you need to add and subtract so that finally you are left with ammonium and hydroxide ions. Getting my point or not?
Yes.
Yes, sir.
So I need to have ammonium ion and I need to have a hydroxide ion. Let me be very clear. Look at the formula which is asked. Ammonium I need a hydroxide. The rest all ions I need to subtract. Okay. So I will add ammonium chloride and I will add NaOH. Ammonium chloride and NaOH. X plus Z. But with ammonium chloride, ammonium I will get ammonium. With NaOH I will get the hydroxide. What extra came in along with it? This is Cl, this is Na is extra. So in order to get rid of the molar ionic conductivity of Cl minus and Na plus, I will subtract the molar conductance of NaCl. Got it?
Yes, sir.
Very easy. Okay. And you will get full score in this. Just be careful which formula to add and which to stop. Okay, so they will give you some certain values and they may give you some extra values also. I have not written the numerical values. If they would have written the numerical, you could have done that also. Put the numerical values. Now other applications of Kohlrausch. Kohlrausch law made our life very simple. For any electrolyte, I can get the maximum value of its molar conductance. I can get the maximum value in infinite dilution when I put it in a lot of water by treating it as ions. So this already we did. I can calculate the alpha. What do you mean by degree of dissociation? I can calculate alpha. Degree of dissociation means out of 1 mole how much extent, what fraction of 1 mole is dissociated. That is called alpha. If 50% is dissociated, alpha is 0.5. If 10% is dissociated, alpha is 0.1. So degree of dissociation, alpha, and finally I can calculate it dissociation constant. Okay. So by how much it has dissociated salt, it is a matter of concern only for weak electrolytes like acetic acid, ammonium hydroxide. It is not the matter of concern for NaCl or KCl because the alpha is 1 and they are completely 100% dissociated. So I can get alpha by at any concentration by taking the given molar conductivity divided by the limiting value of the molar conductivity of that compound. I can get the alpha. Is it clear?
Yes, sir.
Degree of dissociation means how much, by what fraction of the electrolyte is dissociated. So when it was infinite dilution, alpha was 1. And when it is lambda m, okay, take the ratio of the given alpha and given lambda by lambda maximum at infinite dilution. You will get the value of alpha. Once you get the value of alpha, okay, this is from your class 11th, that when you take acetic acid, it is not completely dissociated. It dissociated partially into acetate ion and H plus ion. If you are taking concentration C, out of 1 mole, alpha is means degree of dissociation means out of 1 how much is dissociated. So out of C, C alpha is dissociated, C alpha, C alpha. This is the final. This is the initial concentration. And this is the final. So out of 1 alpha what dissociated, what is left? 1 minus alpha. From C, how much is left? C into 1 minus alpha. How much is formed? So whatever dissociated will that much acetate and that much as H plus ion will form. So alpha C alpha what dissociated this and this. Okay. And you write the equilibrium constant, okay, which is the ratio of the concentration of the products divided by the concentration of the reactants. I started with C, initial concentration of C. Okay. So this is C alpha after dissociation. Okay, one out of 1 mole, alpha mole got dissociated, so alpha H plus and alpha acetate ion. So out of C mole, C alpha got dissociated. So whatever dissociated will get into H plus and acetate. So C alpha H plus ion concentration and C alpha acetate ion concentration divided by the undissociated acetic acid, that is C. Out of C, 1 minus alpha only remains. So it is going to be C alpha square upon 1 minus alpha. Alpha, you can put this value over here. You can put this value and get the expression like this. Is it clear to all of you?
Yes, sir.
Okay. So alpha, normally they ask you alpha, you can no need to mix up all the thing. Degree of dissociation is molar conductance by maximum value of molar conductance. Once you have the alpha, put it in this. And this is how you are going to calculate with the value of molar conductance and the limiting value you can find out very easily from the table which is given to you by taking the sum of the limiting values of the individual ions, and they will give you the molar conductance, given molar conductance at present condition. So take the ratio given by maximum, you will get alpha if it is 0.1. Okay, you will put the 0.1 and solve it, and you can get the value of dissociation constant of an acid. This is known as dissociation of an acid, or it is the equilibrium constant for the dissociation of an acid. One and the same. Similarly, there are compounds which are very less. Okay, like silver chloride, barium sulfate, and when you put silver chloride in water, all of it is going to settle at the bottom. It is not going to come as ions. So whatever the solution is there, that has very little Ag plus and Cl minus ion, because most of it is precipitated at the bottom. AgCl is white precipitate. So you have just very few ions, and if you have just very few ions, it is like infinite dilution. So you measure the molar conductance, okay, and that molar conductance which you are measuring is the direct measurement of the infinite dilution, lambda naught. Is it clear? And lambda naught equal to kappa into 1000 by molarity. Molarity is basically the solubility, how much AgCl got dissociated into ion. So you can get the solubility, right? But this is not that much important. Basic Kulrosh law is very important. Is it clear? So now this chapter is almost complete. We are left with some cells and batteries, okay, and some questions. So almost complete. This is the main part, okay, and some electrolytic conductance. A conductometric titration also we need to do little bit, okay, some corrosion and extra things. We need to have some theoretical topics are pending. Okay, that also we could have completed by today because last class was only for 1 hour, so we were not able to cover up a lot of things. So, but most of the things are covered up, and by the next class, it will be over. Okay, so let me end today's class, right? Just be careful and write your answers very clearly. Okay? Don't use short forms. So let me end today's class and let's discuss the remaining part and let's complete this chapter in the next class. Okay? So bye bye everyone.